Hey, it's Mr. K doing a video for AP Physics 1. We're going to work with a merry-go-round and round and round. And we are going to use some conservation of angular momentum. Before we begin, let's go ahead and talk about angular momentum just a bit. Linear momentum, as we should already know, is going to be mass times velocity. Angular momentum, though, is going to be L. By the way, P and L, I don't know why they use P and L, just go with it. Angular momentum, though, is going to be I omega, and you should be a little bit familiar with the inertia and the omega there. The omega there is the angular velocity, and so anytime we go from translational stuff to rotational stuff, mass will turn into inertia, because we kind of care about where the mass is and how much we have in terms of rotation. Velocity will turn into angular velocity by dividing by r, usually divided by r, wherever you're at. So conservation of momentum and conservation of angular momentum, kind of the same idea. However much we got is how much we got, unless there's an outside force or some kind of outside interaction. And so we could say that the initial angular momentum should be equal to the final angular momentum, just like we can say that the initial momentum is equal to the final momentum. Okay? And then the way that we would change the angular momentum is a change in angular momentum would be due to a torque, and that torque would be applied for a period of time. Just like how if you wanted to change our linear momentum, translational momentum, we would apply a force for a period of time. So just keep that in mind. We're going to be using that a little bit here, and hopefully we can solve this problem for you. So the merry-go-round, 100 kilograms in mass, 2 meters. We're looking down on it. Let's get a person here. We're going to have Abe. So he's going to come in and he's going to jump on to this merry-go-round, probably at the edge. Now, if he were to come in and jump on like this, there would be no rotation caused for this merry-go-round that's, stuck into the ground here. If you were to come in and jump onto the disc over here, then yeah, there would be some rotation in this direction. If you were to come in and jump on the disc over here, there would be rotation in the other direction. And so what that tells you is that due to the conservation of angular momentum, if Abe were to jump onto the merry-go-round and cause it to spin, that means that he would have had angular momentum in the first place. That's kind of weird talking about, but in order for conservation of angular momentum to exist, he would have had to have some kind of angular momentum before he jumped on to the disk to cause it to rotate if the angular momentum is going to be conserved. So, that being the system, let's go ahead and get to it. Again, if you were to go straight on, no turny, and that's just going to be like one of our normal problems that we have done before. So we're going to be concerned with what's going to happen when he jumps onto the edge, and then after that, we're going to be concerned with what happens if he actually moves in. So if you have Honest Abe here, Honest Abe, let's have him hit the top. So if Honest Abe comes in, okay, here. Honest Abe is now a point. So that's him. Abe is, let's make him 50 kilograms. 50 kilograms. And he is incoming with a velocity of, how fast is Abraham here? Honestly, Abe, how fast are you? Some velocity of, he's sprinting. He's got a good sprint to him. So 10 meters per second. Comes in, he's going to jump on to the edge of this merry-go-round. He's going to jump on and stick, and then this thing's going to be rotating. So to jump on, stick, and rotate, then we need to consider what his angular momentum is like in order for this rotation to occur. Okay? So we know that momentum is mv. Angular momentum is I omega. Now, Abe will be like a point mass. So the inertia of a point mass is mr squared. Okay? The inertia of a point mass is mr squared. That also is the inertia of a ring. Let me turn this down. So if we were to plug this into inertia for inertia here with angular momentum, that means that he will have potentially some angular momentum of Abe, and that's going to equal mr squared omega. Well, it's not helping us out very much, but we do know that this thing, whenever it gets hit, it will have some kind of, let's see, merry-go-round, MGR. It's going to have some kind of angular momentum afterwards because we know it's going to get hit and it's going to move, right? So we know that it will have some kind of angular momentum, this, and its inertia is equal to 1/2 its m times its r squared. So it'll get some kind of 1/2 m r squared, and then there's going to be an omega there. So, how could we go from this one to this one? And really we need to look at, we need to look at the velocity. So remember, there's this relationship between omega, the angular velocity, and the tangential velocity, or the edge velocity. So since he's jumping onto the edge, we can say that the angular velocity times the radius is equal to the translational velocity. So as this thing is going to spin around, spin around, spin around, if he was the only one spinning around, his translational velocity, his tangential velocity, the velocity of the edge, would be equal to the angular velocity times r. And that's going to be the relationship here. So omega times r is going to be equal to just straight up velocity, meters per second. And we see that that exists right here. But we're going to have one thing left over, so we're going to have m, r omega is going to be v, and there's still going to be an r there. So the angular momentum of Abe is going to be his mass, which we know, 50, his velocity, 10 meters per second, times r. What the heck is that r? Well, it's going to be the r of where he hits. So that r is going to be 2 in this case. So his angular momentum coming in is going to be 50 times 10 times 2, because that would be the radius that he hits at. That's the spot that he hits at. Now, if we were to say that he hits in the middle, this r would be 0, and there would be no angular momentum, which means that this thing wouldn't spin at all, and that makes total sense. That should match up. So, let's see, 50 times 2 is going to be 100, 100 times 10 is going to be 1,000. So we have 1,000, what are the units? Kilograms, meters per second, and then there's another, okay, kilograms, meters squared over seconds. Okay. Excuse me. So he comes in with 1,000 kilogram meter squared over seconds for the units. I don't really like that unit. There's probably a better one that I'm not thinking of right now. If he were to hit somewhere over here, not really at the tip over here, but more like in the middle, then that r would be lower, and he would have less angular momentum to transfer over, which would make this thing spin less, which does still make sense. So what we're going to do is we're just going to say, hey, this is how much momentum that he has. This is the momentum of the, or this is the momentum that the merry-go-round's going to have. But we need to also not forget that he's going to be on the merry-go-round and spinning with it, right? So Abe will also have some angular momentum post-collision of his MVR, or his MR squared omega squared. We'll use whichever one. I'll go back to the original because we know that these two omegas will be the same. It's going to be easier on the math. So the equation would be, hey, initial momentum, who's got it? Abe. Final momentum, who's got it? Well, still Abe, but prime, it changed. He's going to lose some, he's going to transfer some over to this merry-go-round. Plus the momentum of the merry-go-round. And so that is our basic conservation of angular momentum formula. And let's put some numbers in here. Abe, you have an initial angular momentum of 1,000. You're going to end up with, I don't know, but mr squared omega, so m being 50, r squared being 2 squared times omega. I guess we're trying to find out how fast this thing's going to be spinning after he hits it. Plus the mgr, the merry-go-rounds, let's see, 1/2 mass of that, 100, r again, 2 square it, omega. And that's pretty good. So let's see, 2 squared is going to be 4. 4 times 5 is going to be 20, so 200 here. Omega plus another, I guess another 200, right? 50, and yeah, same thing. So 200 omega, and yeah, 400. There we go. So we are good. They're golden. Oh, what is that? So 1,000 divided by 400 gives me a 2.5. I could have done that. Okay, so of 2.5 radians per second. So this Abraham here is going to come in and he's going to hit this merry-go-round, stick to it. It's going to spin around at a rate of about 2.5 radians per second. Now, what is that in meters per second for him on the edge? Well, we take 2.5. If you want to go back, remember, to the original velocities, we're going to take the 2.5 and we'll multiply that by his radius, which will be 2. So he's moving at about 5 meters per second. So he comes in at 10 meters per second, and he's going to hit this thing, and he's going to slow down to 5 meters per second, and it's going to be spinning like this on the outer edge. Which, not bad, not bad. He's going to do one more thing, though. The next thing that he's going to do is he's going to move in. He's going to move into the inner, the very center of the merry-go-round. If you've ever done that, something very interesting happens. And so we're going to see what that is math-wise. So conservation of angular momentum still applies. And so what we should see is that the angular momentum is going to be all this stuff on the right side, which was 400 times 2.5. So I'm going to just go ahead and use 400 times 2.5 because the initial momentum should still be equal to the final momentum. But right now the initial momentum of this problem is going to be him on the outer edge of the merry-go-round spinning around along with it spinning around. So this math still works out. So 400 times 2.5 times 2.5, 900, 1,000, there we go. So we have, oh, that's exactly how much momentum we had over there. It makes total sense. So we're going to have 1,000 of this momentum, and that's going to equal a new momentum, which should be the same amount, but it's going to be a different setup. Abe, if he were to walk into the center of this thing, his, where was it? His momentum, his mr squared omega, or his mvr, his r goes down to 0. So his angular momentum is going to go down to 0 as he walks into the center of the merry-go-round. Well, it's got to go somewhere, because it's still the sum of all the momentum still needs to equal 1,000, which means that as he walks in, the merry-go-round is going to gain momentum because he's losing it because he's walking in. His R is getting smaller, and as that R gets smaller, his momentum goes to 0. So all this momentum that was there before that was shared between him and the merry-go-round, now it's all going to be the merry-go-round. So the merry-go-round, as we wrote down, has a momentum of 1/2 its mass, 100, times its radius squared omega. Okay, and the only reason we're writing only that is because he's going to have no momentum as he walks in. That's what we want to find out. So as he walks in, we would expect the merry-go-round to speed up because now the momentum is not being shared. And so this omega value should be able to get bigger. And that's exactly what we see here. So again, let's take that 1,000 and let's multiply it by 2. Let's just divide by 100 and then we'll divide by 4. And we get an angular velocity of 5 radians per second. So as he walks in, the angular velocity of this merry-go-round doubles. It goes from 2.5 to 5. And you see the same phenomena happening with ice skaters. You know, the ice skaters start with their legs out or their arms out and legs out, and they spin and they bring all that stuff into the middle and they spin really, really, really fast, and then they let it all out again. What they're doing is exactly this. They're lowering their inertia so that their angular velocity goes up so they can make those rotations, and then they open up their arms again, then they'll slow down so that their inertia is higher, and with it their angular velocity would have to be lower. So interesting problem. Hopefully this helped you out a little bit. There will be many more to come. That's it.